In order to take a look at why some of your roller coasters may or may not have worked as predicted or as effectively as you believe they would, we need to look at what's known as the concept of work. And work is basically just changes in energy at its core, but work can be one of the most confusing concepts due to its everyday life use, the way we use that term in everyday life, and how we actually use it in physics and what it actually implies in physics. So if we're looking at everyday life, the term work, probably when you've heard that before, you think of it like I have to go to work, I have a lot of work to do tonight, and we think of things like if you worked at a supermarket, and you have to go to work, you have to earn your money, all that, expend energy, etc. This little picture here, if you ever worked in customer service or anything like that, or at a supermarket, you certainly understand this whole diagram. Um, I guess if you enjoy hard candy as well, you also enjoy this diagram, but that's not here or there. Everyday term work just means like I have a job to do, and that's where a lot of this confusion comes in. As with everything else in physics, the actual physical definition is much more specific and less straightforward. So that's everyday life. I have to go to work, do this, do that. In physics, the concept of work is actually an increase or a decrease of energy resulting from a force that acts on an object over a given displacement. So as I said, that's a very specific term. When a force acts on an object over a given displacement, it will either add energy or take energy away from an object. It's the whole reason why things begin to move, or things like a roller coaster initially get some energy. So if you've ever been on a roller coaster and you kind of go up that first hill, they pull you up that first hill, and then you go through the rest of the ride, work is being performed on that first hill. There's some kind of gasoline being burned or electricity. Something is being consumed, some form of energy to get you to the top. That's what work is, okay? But we're going to look at it in a little bit more detail, so hopefully it makes a little bit more sense. I think the easiest way is to look at an example. So if we take a look at this example, very simple. I have a box that's sliding to the right, and it comes to rest with a final velocity of 0. At this point, you should all recognize why that occurs. There's friction between the floor and the box. If you ever slid something across the floor, you've always seen it come to rest due to friction. So if we look at the box beforehand, it has a certain amount of kinetic energy because it's moving. At the very end, it's no longer moving, so it has no kinetic since it has no velocity. It has no height, so it has no gravitational potential energy. And there's no spring anywhere in this diagram, so there's no elastic potential energy. So I go from kinetic energy to no energy. So what exactly is going on here? Because this violates that whole law of conservation of energy. Whatever we began with, we have to end with. So what actually happened here? Okay, it seems like energy has been lost, so to say. I had some kinetic, now I have none. Really what's happened is energy has been removed due to the concept of work. So what actually happened? Well, if you look at it, friction is a force. It opposes the block's motion. So the force is going to the left, but the displacement is to the right. So it's fair to say that the force of friction acted on this block over a given displacement. Now, since the force and the displacement are in opposite directions, that means energy was removed, okay? That doesn't mean it's gone. That means it's left this system. It's no longer in the box. It leaves in the form of what we call dissipated energy. And dissipated energy is just any energy form that is not mechanical. It's not elastic potential. It's not gravitational potential. It's not kinetic. In this case, if you rub your hands together, you'll generate a lot of heat. So friction will generally transfer that energy out of one of those mechanical categories and into something like heat or sound, something like that. That's what we mean by dissipated energy. So did I actually lose this energy? No, it's just that it's no longer in the block. While the block was originally traveling with kinetic energy and it lost all of that, in reality that energy became heat and escaped, it became sound and traveled away, but the block no longer has any energy. It's lost it to its surroundings. Again, in the form of what we call dissipated energy, but again, that just means heat, sound, other forms that are not actual potential or kinetic energies. That's all dissipated energy means. So if we look at another example, just to kind of reinforce that, I have a block that's at rest, someone gives it a shove, and now it travels with some velocity. Well, beforehand, again, it's not fair to say it has no energy, but it has no mechanical energy. It has no velocity, so there's no kinetic energy. It has no height, so there's no gravitational potential energy. And there's no spring, so it can't have any elastic potential energy. After it's been shoved, it now has kinetic energy. So the question is, well, I had none, now I've gained some. Where did this energy come from? Well, what happened was there was an applied force acting on the block, and there was a resulting displacement. Now, in this case, since the force and the displacement act in the same direction, that means that energy has been added to the system. So you'll see I had no energy. The force and the displacement were in the same direction, so I gained some form of energy. My previous example, it's the same concept, but because the force and the displacement were opposite, energy was taken away. So I had some energy, and then it was removed. Again, this means mechanical energy. I didn't lose any energy, I've just changed form. When we say no energy, that just means we've changed it to some form that does not fit into the classification of mechanical energy. So I've lost that to heat, light, sound, something like that, that we don't consider mechanical. It travels off to some other system. Okay, the two questions you should always ask yourself to figure out whether work has occurred, and these are important. The first one is, has energy been removed or added to the system? So if I look at any of my examples and my pie charts, my energy charts, it seems like I've magically gained energy or I've magically lost energy. That's a number one sign right there that work has occurred. Something has either added work to the system or it's removed work from the system. And the second thing was, has a force acted on the object over a given displacement? Okay, if there's a force and a displacement and they act in opposite directions, energy is removed from the system. If the force and the displacement act in the same direction, then I have... No, you may not.
Please report to the front security desk. Mr. Richard Burton, please report to the front security desk.
Thank you, Richard Burton, for ruining my video. All right, the second question, as I said, if they act in the same direction, energy has been added. If they act in the opposite direction, energy has been removed. So the general idea here is to just consider if energy magically appears or disappears and take a look at the displacement and the force. Now the last thing I want to just briefly mention, I keep referring to this term system. Some of you may be confused by that, so very quickly. Defining a system, well, system is just the group of objects selected for a particular analysis. So I'm going to show you 3 different ways I could define this system and just show you the differences in each. So a very brief example, I have a box that's traveling to the left, and it's going to hit a spring that is initially uncompressed, and then it's brought to rest as the spring is compressed. Now this system, I as the scientist get to define it. I'm going to say that this system is the box and the spring. So I consider the energies of both of them. So this has no energy initially, this has kinetic, so combined the two of them possess some form of kinetic energy. Afterwards, this no longer has any kinetic, but this now has some elastic potential. So together, I have no energy and elastic potential, so I have elastic potential energy afterwards. I haven't gained or lost any energy, I've just changed its form, so no work was performed because I don't have a change in energy. I have a change in form, but I don't have a change in the amount. I had kinetic, now I have elastic potential. It's fairly straightforward. If I take the same situation, but I instead say my system is only the box, that means I will only analyze the box. It doesn't matter about the spring, I pretend it doesn't exist. So if we look at before, the box just has velocity, no height, the spring hasn't been, there's no spring in the box, I'm just looking at the box. It has velocity, so it has kinetic. Afterwards, the block has no height and no velocity. Yes, it's compressing the spring, but if my system is just the box, that's the only thing I look at. So the box went from having kinetic energy to having no mechanical energy. That's a sure tell sign that work has occurred. And if we look at it in more detail, the block was moving right as it hit the spring, but the spring exerted a force to the left. Since the force was to the left and the motion was to the right, opposite directions mean you should lose energy, which is exactly what happened. I had kinetic. It was removed from the box by the spring, which is exactly why the spring now has energy and the block doesn't. If instead I define this same exact scenario, but now the system is going to be just the spring, I ignore the box. So prior to anything happening, well, the spring is not compressed, it has no energy. I don't care about anything else because my system in this case is just the spring. Afterwards, the spring is compressed. We don't care by what, we don't care what compressed it, I'm only looking at the spring. So originally I had no energy in the spring, something compresses it. Again, this magical gain in energy, so to say, is a sure tell sign that work has occurred. First of all, I seem to have gained energy, meaning I have a change in energy. And the other thing is if I look, well, the spring experienced a displacement to the left. It got compressed to the right, it got compressed to the right. The block exerted a force pushing to the right. Since the force from the block and the displacement of the spring are in the same direction, that means I get a gain in energy. So this idea of a system, you define it as the scientist, as the physicist, and then you just have to decide, am I considering everything, just one object, just the other? And you can clearly see here that choosing different systems will produce different outcomes. It's the same exact scenario. It just depends on whether you're looking at specific objects or groups of objects, and you get to decide as the scientist which you would like to do. There are advantages and disadvantages to either, and we'll take a look at some of these down the road as we explore energy further.